All right. Hello, my name is Craig Roy. I work on compilers and programming languages at Quantinuum, along with these three other people. Together, we are Team BRAT. That's a functional programming language we're writing for writing quantum programs. But that's not the topic of this paper. This paper, I'm going to present an equation solver for a subset of the natural numbers that we intend to use in our language. This is has Conor at the heart of it, which will become very clear if you read the paper. The title is enough. Right, so we're going to pick a subset of the natural numbers, prove completeness of equation solving, and in order to demonstrate this, we've cooked up a small programming language called Foobarn. We did this because we're writing our programming language BRAT, which you write quantum programs by metaprogramming, writing classical programs that write quantum programs. The goal is to classically make guarantees about the safety of the things that you're going to run on the device. And our abstraction is that we have vectors of qubits, and you're applying operations to those, which has got us interested in ways to talk about vectors. Our users have programs that have lots of structure, so we want to provide ways for them to express their structure in our language, ideally. Also, because we're a quantum programming language, we have linear types for qubits, which we'll go into in a minute. But this is our little language. It should be easy enough to intuit for this crowd, I hope. The main thing is that we have functions indexed by type level numbers. And we have built-in vectors, which are written n of x, n of y. We have polymorphism over types as well, but there's nothing novel about that. And in the clauses, you can pattern match on the numbers. And we have fancy vector patterns. This is just cons, but it's written in a weird way. This comes from Conor's experience teaching in university, where people are always confused about, first-time students are always confused about which is the head and which is the tail when the operator is symmetric. So we have a point to note the element and then an arrow to the long part. And in our language, we can infer all of these numbers, so you don't need to write them. Right, and we're interested in equation solving for a couple of reasons. When we want to type check functions like this, we look at the clauses so that we can check that the patterns make sense against the number arguments that we expect, and we can create refined number variables to use on the right-hand side. For example, if we use the nil pattern, then n must be 0. If we use cons, n must be a successor, which we write as a big red S. And when we're making function calls to type check this, you have to make sure that the number that you pass in matches the type, the argument type of the function you're calling. Here we infer head m, but we need to check that m is a successor because head expects a successor n of x. And this is what a vector of n plus 1 x's looks like, Sn of x. And when evaluating, we also use this to choose which branch to run. So we're interested in equation solving, and this is not an important example. This is just something we do right now in BRAT. We have vectors of qubits, and qubits are linear. We can do a big fold over our whole list vector of qubits, and that's great, but cons can only get you so far. What if we want to look at something in the middle? Do something like split at in Haskell. It's going to be a pain to guarantee that it's safe because you pass in a runtime number and you have to guarantee that's less than the length of the list. So we want something better. So You'll recognize this from Satnam's keynote yesterday. This is Batcher's merge sort. We're not specifically geared to quantum. Anything that has a divide and conquer structure, this will be useful for. In particular, quantum programs and classical circuits or digital logic are inherently parallel, and that's the kind of angle we're going for with this solver. So the important thing about the merge sort is the structure of the algorithm is recursive. This big red box is sort n, and we have two implementations of sort n minus 1. We split our inputs in half and pass each into sort n minus 1, and then collect them all together in a big merge box. This is n equals 3, and you can see we have 2 to the 3 inputs and 2 to the 3 outputs. And we can go one level deeper for illustration. Each sort n minus 1 contains 2 sort n minus 2s. And then at the bottom, we have a bunch of these compare and swap elements, which is just something that's passed into the function for whatever type that you're calling it on. Compare and swap takes 2 arguments, compares them, and swaps them so that they come out in a sorted order, but it's always for 2 elements. And we can write this in our programming language. This is just another level deeper with all the detail. This is the version from the paper. So you can see the wires a bit more clearly. So in our language, you can take the type of sort. As I said, it takes 2 to the n inputs and has 2 to the n outputs. We're taking some compare and swap thing. But what's going on with the vector pattern in the middle? On the last line, we have sort cast t, x's equals and equals y's. We call this the even pattern or operator. And what this is doing is splitting everything in the middle. And the second part of this is the merge, which takes two vectors of size 2 to the n. And the details aren't important, but we have another operator on the third line. We're using this equals percent equals pattern, which does something slightly different, but also needs to guarantee that we have an even length vector as the inputs. And there's lots of crazy patterns going on, but that's not important. Our full list of vector patterns in the language that we've found to be useful for this. On the top, we obviously have the empty vector, cons, and snock, which have the same types, but elements swapped around. And then on the second row, these are our novel operators. The first one I call even, then riffle, then odd. The first two have the same type signature, but odd requires an odd list, or an odd length vector. So the type at the end is successor of double of n, as in anything times 2 add 1 is going to be an odd number. And this is the illustration of the semantics. For odd on the top, we have a black element in the middle, and then blue and red things, and they all slot together. The ampersand thing is just meet in the middle. And then the percent sign is less intuitive. It takes all the even elements and the odd elements and alternates them to build up the list. I think Satnam referred to this as the butterfly operation. Close enough? So this gives us a bunch of equations we want to solve if we want to be able to type check problems like these. We need to know if things are even or odd, check if they are, if our inputs are 2 to the n of something. And in picking a way to represent these equations, there's lots of arithmetic out there. So we've applied a bunch of prejudices to reduce the search space and decided that things are easiest if we keep it to monotonically increasing functions in one variable. Obviously, the way that this is usually done in dependently typed programming languages is you have functions in any number of variables on the right-hand side. So, for example, concat has output type of length x plus y. We want to avoid that because it's very complicated, and we want to keep things easy for ourselves and mechanizable. So in order to write the type checker for this, we have a bunch of helpers. Unz is asking if a number in our language is z. Our language here As has been alluded to, we have 0, successor, and double. Successor in Z has no solution, which we represent as nothing in this pseudo-Haskell, just in black and white, because I don't know how to use the syntax highlighter. I didn't write myself. But double is 0 when it's double of 0. And we can peel off successors and doubles as well. The part to keep an eye on here is the successor versus double case, because then we have to add 2 constructors instead of just 1. For example, on the bottom left, if we're taking the predecessor of a double, then we have to half it, take double, sorry. We have to half it, take the predecessor of that, and then double and add 1. And this is kind of unsatisfying because the rest give us just one thing or nothing. So we add an extra operator called bubble, which is definitionally just successor of double of something. And this makes things a bit nicer, namely the lines in blue. And we can easily write the unbubbling logic. So now if we want to add power to the language, things get interesting. At the start, it's easy. Is power 0? Never. By power, I mean 2 to the n of n. So pn is 2 to the n. Undoubling, that's easy. That's just p to the n minus 1. And unbubbling is only valid when it's 0. But writing the predecessor of power is quite tricky. So we could have something like adding power of n minus 1 for all the predecessors of n, but then we have many powers of the same variable, and we want to keep things to just lists of one function in that variable, all composed with each other. So it turns out what we want is actually to take the predecessor of double and put that in our language. So that makes things much easier to write, and this is the key observation of our paper, that full is much better behaved than power. Why is it called full? If you think in binary, 2 to the n minus 1 is all of the ones for your vector of bits, versus power, which is just 1 followed by a bunch of zeros. So we call this full, and it behaves very nicely with our other operators. Full of n is 0. If n is 0, I've cheekily added an effect to the fake Haskell here, because if we get to this case, then we can define n to be 0. We want that to bubble up to our unification environment. And it's a little bit nasty. Well, what's nice is that bubbling full gives you the next full, as in the un-s case here. But what's not nice is that we have to add 2 constructors there, which we would like things to be nice and uniform, and it's only pop out 1 constructor, but what can you do? Normalization of these things is fairly easy. We just have a couple of rewrites. We push all of the f's inwards. We pull all the s's outwards, and we have the d's in the middle. There's a nice proof of this in the paper, that we only have to prove that they align for I equals 0, 1, or 2 to have to be the valid normal form. But now the more important part is we want to prove that we have complete equation solving. That is, for every 2 numbers in our language, every equation of 2 numbers, we can put out a solution. And moreover, we can spit out the best solution. So the way that we prove this is we have a subset of a subcategory of set, I suppose, with the empty set, the unit set, and the natural numbers. And we take all of our SDBF constructors as arrows from n to n. we can always produce a Z if we have upside down exclamation mark, which I should have thought of a name for. Let's call it GNAB. That means that we've failed. There's no possible solution, and that's a valid, that's an expression in our solution language that there's no possible way to unify these two things. So you should give up. And identity arrow, obviously. So, yep. So for example, the way that we're talking about this in terms of pullbacks in our category is if we have an equation like dn equals fm, then we model that as two arrows pointing into the same target, and then we draw the pullback with the arrows that would have had to be, so that it's the most general solution and not just a random unifier. So the top case, full of something is equal to d of something only when the two things are the same and they're both 0, is how to read that. And the bottom thing we have is successor of n equal to 0, no. So a couple of upside down bangs as the arrows. And the observation is that the tricky thing about our equation solving is full, because if we try to take the predecessor of full when we come out with two constructors instead of just one, as with every other case, if every equation gave us a pullback with one thing on the arrow in the result, then we could tile everything squarely and it would all be fine. But we have to work a little bit harder. So we observe that we can express all sequences of arrows in coin, not ZSDF. In our category of solutions, all sequences of arrows can be expressed as a bunch of these nice, well-behaved arrows, lowercase f, followed by one problematic f, which can be these sort of bottoming out cases. Identity where it's equal to some number, or it's impossible, or it's 0, or it's full. Okay. So if we can solve for one of these things, then everything we can express is a sequence of these things, and it all composes, and we're happy. So what we need to do to prove completeness is fill in this square, and I have less time than I thought. So the first thing is well-behaved things are well-behaved. So we just get more well-behaved things out. And then when we pit them against less well-behaved things, then we either get a double at the start or we don't. So pulling back this G star along F on the top, pulling F along G star gives us S, which can be a double or no double, followed by a badly behaved thing. And we can tile out rightwards and downwards with that because it's symmetrical. And these double or not double, they spit out things of the same length, the same amount of doubles on the head. And we have a couple more lemmas, followed at last by poorly behaved things solving for more poorly behaved things, which completes the square. And we're happy that any equation that we can express in the language can be expressed as f, small f after big F, composed with a bunch of those. And if we can fill in the square for that, we can come up with a solution for everything. This is a quick outline of how we implement this in a unification algorithm. We just call out to the unz, und, unb things that we had before. There's a couple of extra things here like numdef, which is just defining numbers in the environment. And we're spitting out delta, which is a refined context. And we have a proof for this, we have this implemented in Rock. And we made the termination checker happy with this measure of progress, which isn't the nicest thing, but it works. So things are always getting smaller, but not always in the same way. So rounding up, We tried other approaches, like all of the GHC extensions that Satnam showed in his keynote, and they fell over on the more involved cases when we have nesting of multiple fools. And things like SMT solvers, they don't have the completeness property, so when we put in more complicated equations, they fall over at some point, whereas ours doesn't. In our language, we have existentials, and the solver is just as good at working out what the output should have been, what the output should be as it is what the inputs should have been. Future work is there's no reason to fix doubling and power of 2 as our base. If we could do this for every prime number, we could have more numbers in the language, and everything is proved in the all of the proofs that I mentioned are in our artifact. And that's everything for me. Thanks.
I would like to invite anyone with questions to queue up on the microphones.
Thank you for the entertaining talk. Isn't it a bit sad that you cannot have a sum, as you cannot concatenate array, like shapes of arrays?
So we're taking a very principled isn't the word, strong-headed approach, that doing things like concatenation is throwing away structure, and if you have a pair of vectors, you can keep it as a pair of vectors, and then it's more representative of your problem.
And what if you want to map over those vectors? Then you have to keep writing helper functions that will do it for 2 and 3 and 4 vectors at the same time?
I think we can solve that problem.
Cool.
But we have other things going on to address mapping over vectors.
All right, thanks.
Thanks.
Yes. Okay, in that case, I'd like to ask one. Maybe, sorry, this is going to be an annoying logician's question. Essentially, what you're doing is you're deciding a very, very little fragment of arithmetic. Is this a known fragment? Is it something that people have identified before? Is it just something that was useful for your particular application only?
I don't think it's been done before, and it's a step up from using Pressburger arithmetic. So anywhere you want to slot in an equation solver, then you can safely put in this one.
Thank you. All right.
I can ask a second one, since you mentioned Pressburger arithmetic. In terms of the complexity, is it sort of comparable to Pressburger, so doubly exponential, or is it? Have you considered any complexity results for solving in this language?
No, we haven't considered the complexity, only completeness and termination.
Okay.
So we don't have actual performance or complexity information.
But if it's a step up, then probably it's at least doubly exponential.
Step up in terms of expressiveness, I mean.
Oh, I see. Okay, cool. Thanks.
For something that's complete and decidable.
What were normal forms? Are they just SSSSZ, or you have?
So you're putting all of the. You're not mixing constructors together. So any number of S's, which you can just represent as in binary in your programming language is n plus, and then the rest of these things. Then you have a number of doublings, and then some number of fools. So they're all getting sorted into their own little buckets, S's, then D's, then
But
S.
some of these are equal, right? So or is this unique? Are these normal forms unique?
Sorry, I'm not sure what you mean.
I mean,
like two
they represent
equivalent
natural numbers. Aren't there two natural numbers which can be represented? Isn't there a natural number which can be represented by different normal forms?
So they're not natural numbers, they're like equations in natural numbers. So any two terms which are equal for all natural numbers have the same normal form.
Okay.
And vice versa.
Please join me in thanking Craig once more.